All right, welcome back. So in this video, we will continue talking about the instruction set. We have already covered the data movement and the arithmetic instructions. Today we're going to be talking about the logic instructions, a little bit of bit manipulations, and rotate instructions, C3. Okay, so let's get started with logic instructions. Logic instructions, as you might expect, they covered logic functions like AND, inclusive or you can just call it OR, exclusive or XOR, and not, or the complement sometimes it's called. And as you might expect, the instruction set actually has the name AND in it. So AND L and W, that means, well, it'll take the AND, and it's a bit by bit. So these all operate on 8-bit data, so it's going to take bit 1 with bit 1 from the other word, bit 2 and bit 2 from the other words, and ANDs them or them or XOR them, or actually just take their complement. So as you might expect, anything that has the letter L in it, like AND LW, that means I am taking the content of the working register and ANDing it, basically doing a logic AND with some sort of a literal. A literal is just a constant on a number, and that number is K. I can do it between the working register and some sort of a data register or file register, basically a row in memory, and that's I can provide the address for that data, and I can specify the destination, whether I'm using access bank or not. Kind of like what we saw before. What I will do right now is I'll just go through some examples to show you how we use these. The rest of the inclusive OR and the XOR are exactly the same. You have one with literal, so it takes a constant with the working register, or take a location of memory with whatever the content of the working register is. Okay, so let's go to MPLAB and just do a few of these examples. Okay, so we're gonna give a few examples about how we use the AND or XOR and not. As you might expect, they're gonna operate exactly how you expect them to operate, but I'm just gonna give you how useful they are. So the first thing we can actually test, maybe we can test the content or the value of a certain bit in a location. So let's do this. For example, we can say, well, let's move some value into the working register. In that value, I'm just going to type it in binary because it's easier to see. 0 1 1 1 B. This is basically when I specify B after I'm telling it this number is binary. Okay, and now this will be in the working register, so I can easily just take the first instruction, which is N and LW, and provide some sort of a thing that I want to AND with that particular number, bit by bit. So I'm going to take AND LW, and the value I'm going to AND with is 0 0 0, depending on which bit I want to test. Let's assume that I want to test this the bit I'm actually under. So what I'm going to do is I'm going to put 1, and then I'm going to put 0 0 0 0, and that is also a binary. So when I take the AND of these two numbers, of course AND 0 with anything is going to be 0. So the only one that actually matters is whether I'm ANDing this number with this particular bit with the PID right under it. So if they happen to match, that means the answer will not be a bunch of zeros. It will be a bunch of zeros and then 1 and then another bunch of zeros. This is the exact same number. So the last answer is not going to be 0. So we're going to see that the content would be reflected in the Z in the 0 flag in the status register. So let's debug this and let me show you. Okay, so we're gonna do that. Okay, so it got debugged. Okay, we'll do this, and then we're gonna see it. We're gonna go through it one by one. So the first row, let me just expand it a little bit so we can see all these controls. We're gonna step through it, and as we have expected, it put that particular value that is in binary in the working register. It just happened to be B7 in hex. I wrote it in binary because it's a little bit easier to see. And now the next instruction, what it will actually do, it will take that and it will AND them bit by bit. Okay, and the answer would be stored back in the working register. Okay, so I will actually go step through it, and you can see what I got with inside the working register is I got the same exact number here, which is basically 0 and 1, and that's exactly what it is, 0 and 1 hex. Okay, what matters to me is the content of this particular bit I'm testing is 1. Okay, that means the 0 flag is down. So the 0 flag is opposite to the value of the bit I'm testing. So let's change this example a little bit. Let's assume that I want to test this particular bit, okay, and I know that it's a 0. So what I will do is I'll go through it here, and then I'm going to debug it. Should have probably just pressed the debug. Okay, and then I'm gonna go through it. This is the same exact value in the working register. And then when I AND it in here, I know that the AND between these two numbers is gonna be complete 0 because the bit I'm testing is 0. Okay, so you can see that the Z flag here is actually high or up. Okay, so the status flag tells me that the last operation you did resulted in a 0. That means the test or the bit you tested happened to have like the value 0. So why is this useful? Well, it's useful because we might just test the least significant bit, for example. So the least significant bit, usually if you test it and happen to be 0, that means the number is even. If it happened to be 1, that means the number is odd. So without even knowing what this number is in decimal, I can tell you it's an odd number because its least significant bit is 1. So if I do this and I just basically go through that one by one, all right, so we go through this, we go through that. The Z is actually down. That tells me the last value we tested, or basically the least significant bit, happened to be 1. That means this number is odd. So I just basically created a test for even or odd. And of course, based on the value of the Z, we're going to see it later. We can actually branch. So if we can say if a branch if not 0 or branch if 0, and we can jump to a different location. This is basically an if statement. We're going to cover it next actually in later videos. But for now, we know that we can use the AND operation to do these type of tests. Good. Okay, so what else can we do? Well, it turns out to be that we can actually use something we call a mask. So generally speaking, what you AND with is called a mask, and some masks are a lot more useful than others. So for example, let's move a different value into the working register. So let's say 0x25, and let's assume that for the sake of argument, I'm gonna, just so that we can actually use something else beside the AND LW, I'm gonna move that value into memory. So I'm gonna just say move from W to F, okay, and I'm gonna say I'm gonna put it in location 10, and the destination is gonna be the file register and then access. So here what I'm doing is I'm storing the value 25 in location 10 in memory. And this way, because I want to show you how we get to AND WF, like how do we use this, how different is it from AND LW, so that my example is a little bit different. Okay, so now what I'm going to do is I'm going to move LW, which is the mask that I'm interested in ANDing with, okay, into the working register, and my mask happened to be 0, 0, 0, 0, and then 1, 1, 1, 1, or you can just write it as 0x, 0f. Okay, so basically if I AND anything with this particular mask, what I will be doing is I'll be keeping the least significant 4 bits, and I will be zeroing out the most significant bit, the 4 most significant bit. This is very interesting if I'm dealing with some BCD and I'm interested in a part of it, not the other part. So if I AND that value, which is 25, stored in location 10, with that particular value in here, I should just get the 5. It's going to give me 0, 5. So let's see it. So so my working register have the mask. I will AND my working register with some sort of a location in memory, and that location happened to be 0, 10 or x 10 actually. And I want, so it's up to you to whether you want to store that value inside the working register or not. Let's assume for some reason I want to keep that mask because I'm going to keep using it. So I'm going to give it back to the location because I'm not interested in the value 25. I just want it basically to get rid of the 2, and then the access memory in here. So we do this. Okay, so let's go through it one by one. So we're gonna go through this row, and then location 10 has that value 25 in hex. And now I'm gonna go through that, and it tells me, okay, I put that particular value, move LW. Let me just see, did I 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that working register should not be 5, 7. Okay, let's pause and let me pause and see what happened. Okay, so I figured out what the error is. The error is I keep doing this. Remember, I didn't specify what the radix is. The radix should be a B in here. I should tell it that this number is binary. If I don't, it will consider it as decimal. So it converted this big number into the decimal, and it just turned up to be 57 for some reason. Okay, or 57 hex, that's how it translated it to. So if I actually do it one more time, this is actually a common error. I keep doing it over and over, so I'm glad that I get to show it to you now. Okay, so we're gonna go through it. We're gonna step 1, 2, and you can see it now. It's actually 0. It's basically 0f, exactly what I expected it to be, because I specified that this number should be in binary. Okay, So 0x is hex. You don't have to put the h at the end, but if you are using binary, you have to specify binary at the very end of it. Okay, so now we know that the working register. Okay, so now going back, I know that location 10 has that 25. The working register has my mask, and now I'm gonna AND them. And ANDing them, I know that I'll be keeping the least significant 4 bits, which is just a 5, and I'm gonna store that value back in the location. So after this instruction is implemented, you're gonna see that this 25 becomes a 5. So let's see this, and that's exactly what happened. It became 0, 5. So this actually mask is very, very neat and important. Sometimes you want to isolate certain bits within a word or within a byte or something. We can actually use it. Okay, good. So this is in terms of masking or keeping certain things. But what if I really want not necessarily to mask it, to zero out certain things? Let's assume that I want to make certain bits a bunch of ones. So let's assume that I want to transfer this 25, or this, instead of having it 0, 5, I want it to have F5. I want all the values at the very top to be ones. So, okay, what I would do is I would say 1, 1, 1, 1, okay, and I can just say 0, 0, 0, 0, and this is exactly as saying, well, this is F and this is 0 in here. That's what I'm doing right now. So now I'm gonna move the value 25, put it in 10, and now what I'm gonna do is I really want the upper 4 bits, these two, I just want to get rid of it, and I'm gonna make them an F, or a bunch of ones. All I have to do is just, instead of ANDing, I can just OR them. So an OR between a number and another one is just ones. So if this is my mask and I'm ORing 1 with anything, it's just gonna set it to 1. And if I'm ORing 0 with anything, it's just gonna keep it not change. So I'll be keeping the least significant 4 bits, but I will be just setting the most significant 4 bits to 1. So let's do this here. Let's see if that will happen. Build fail. Okay, because it's actually called inclusive OR. That's how we have to see it. Okay, the instruction here is inclusive OR, not just OR. Okay, we do that. Okay, it builds it, and then we're gonna step through it. 1, 2, and I know exactly now my mask is F0, and look what happened in here. See, the location memory 10 is have 25. It's after I implement this instruction, it has to be 10, 5. Or basically F5, sorry. So it's F5. This is exactly how I would say it. So if I want to set any bit for that matter, it doesn't matter. Let's assume I want to set this 1 bit in here. I want to not set this one. I want to keep its value. So you can create whatever mask you want. And if you OR that mask with something else, you will make that bit that you set in the mask to 1. The output will be 1, and it will keep anything else as 0. These are very, very useful when we're talking about outputs, when we're going to be dealing with connecting the pins outside to something else, like for example to LEDs or something like that. And it appears not only microcontrollers and a lot of programming things as well. Okay, so this way we learn how to set certain bits to 1, and if we want to set certain things to 0 instead of the OR, we actually put it to AND. So we can do anything we want with it. So how about if I want to toggle all the bits? For example, I want whatever this value here, it's 25. Let's write it in binary so you guys get to see it. So 25, I'm going to write it in binary here, which is 0, 0, I think 1, 0, and then 0, 1, 0, 1. Okay, and that is in binary. So this is basically the same number. I didn't change anything. I just wrote it in binary. Okay, and I'm gonna just use capital B just to be consistent. Okay, so we did this. I wrote it. Let's assume that I want to switch every 1 to a 0 and every 0 to a 1. I want to complement it. Of course, you might tell me, well, we have the not or the complement in here, but it's like this is totally valid. So why don't we do it this way? Let's assume that I want to toggle not all of them, just the least significant 4 bits. So I don't want to use the complement F. I don't want to just take the 1's complement of it. I just want to keep the 1's at the bottom. So what I'm going to do is I'm going to say 0, 0, 0, 0. These are 4 zeros, and 1, 2, 3, and 4 bits. Okay, so this number is technically 0 in F. Okay, so look, what I'm really interested in is switching this 1 to a 0, 0 to a 1, a 1 to a 0, and 0 to 1, and I want to keep these upper ones. So the answer should be, it's going to be 10, I think so. It's going to be 2A. That's the final answer that I'm looking for, just by toggling these. So toggling happened to be implemented with an XOR. Okay, so I'm doing an XOR because an XOR 1, and if you basically take 1 XOR 0, the answer would be 1. So you keep it. Okay, And if you do 1 or you do 0 or 1 XOR 1, the answer would be 0. Okay, so if the bit that you want to toggle is here, okay, your mask has the value 1. So whenever you XOR something from your mask, which is 1, with a 0 in the value that you're trying to toggle, you're going to see that the answer got flipped. So if your mask has a 1 and your bit value in the register you're interested in has a 1 and you XOR them, you get 0. So you're basically toggling them. So if I implement this, I'll be toggling these 1s, 0, 1, 0, because my mask has a bunch of 1s in here. However, if I do my mask now, I'm going to change my mask and I'm going to put 0 in that mask and I'm going to put 0 in here. You're going to see that 0 XOR 0 is going to be 0, so you keep that value, and 0 XOR 1 is going to be 1, so you keep it. Okay, so this mask in here, supposingly if I do it between the value in here and the value in the mask and I XOR them, I will be just toggling the least significant 4 bits. So let's test that. Okay, so we do this. We step through it. 1, 2, and exactly what I wanted. This is my mask is now in my working register. Okay, so now if I toggle them, I should expect the 2 to stay the same, but the 5 will be flipped, so it's going to be a 10, which is an A. Good, so 2A, and that's exactly what happened. So these are very useful. So what I just showed you right now is I have some sort of a mask, and I can AND, or the AND, whenever you see a 1, it will keep it. Whenever you see a 0, it will 0 it out. If the OR is completely the opposite, whenever you see 1 in the mask and you OR it with something else, it will set it to 1. The 0 will keep it the same. If you have an X or whatever you see a 1, it will just toggle it. It will just basically flip that bit. Okay? So this is something very useful, and it turns out to be that we can also use these XORs and and OR to set one single bit. For example, let's assume that I really want, like, from this value in here, I just want to clear that particular bit in here. Okay, I just want to clear it. So I'm going to go to my mask and I'm going to say, okay, how do I clear a mask? Usually if I end it with a 0. Okay, so I'm going to put a bunch of 1s, 1, 2, 3, 4, and then 1, 2, 3, and then I'm going to put that 0 in here. This way, well, let's do it like something inside. So 1, 2, and 3. Let's assume that I really want to 0 out this bit, which is 0, 1, 2, bit number 2, which is the third bit. So because we start from 0, 0, 1, 2, I want to 0 that particular bit. So what I need to do, this will get stored as usual. It will get stored in that location in 10. And then here is my mask. Okay, my mask. Let me just write that this is mask so that I don't have to convert it to hex all the time. And now if I take this and I will be keeping the original value, but I'll make sure that whatever bit comes here, which is bit number 2, will get to 0. So I'll be converting that number here to 0. And if you think about it, that will become in hex, that will become 1, 2. So I should get something like 21 in hex. So let's do that. So we can do, instead of XOR, I'm going to do AND. And there you go. So what I'm doing right now is I am clearing a certain bit. Okay, so I am clearing a certain bit. So we'll do this here. And my working register has the letter FB, which is correct. And then I will do that particular instruction, and I got the 21 exactly how I expected it to be. This way I clear this particular value in here. Okay, so if it was a 1, it becomes a 0. If it's a 0, it still becomes a 0. Okay, let's assume I want to do the complete opposite. I want to set a certain bit to 1. Okay, and of course you can do this for multiple bits. Let's assume that you want to also 0 out this bit, and you want to also 0 out this bit. You just basically take the AND with it, and you can 0 certain bits in. Let's assume that on the opposite, what I want to do is I just want to set a bit to 1. Basically, I want to make sure that it's 1. So I'm going to create a different mask now. I'm going to put a bunch of zeros in it. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And let's assume that I want the second, basically bit number 1, to be set to 1. Okay. So now what I need to do is I just need to do the inclusive OR between them. So if I take that or this, I will be setting this particular bit location to 1 no matter what the value is. So, and let's think about it, that becomes a 1, 1, 1, which is a 7, and that stays 2, so I'm looking for 27 in hex. Okay, so we do this, we test it, and I'm gonna go through it here, and once I apply it, okay, once I apply it, we get the 27. This is exactly what I expected. So the AND is useful for clearing a bit, the OR is useful for setting a bit to 1. How about the XOR? Well, if you do XOR instead of inclusive OR, well, guess what? I'm going to use the same mask. You will be just toggling whatever is here. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. So I'm expecting to see the same exact answer right now. I should get the 27 because if I switch the 0 to a 1 because I'm toggling it, I should get the same number. So we'll do this, and I got 27, which is exactly the same. I recommend that you play around with them. They're really, really useful. These logic operations, they're extremely useful, actually. All right. Okay, so now we go to the other set of instructions. Okay, so we've seen logic instructions. Now what I want to do is I want to show you bit manipulation instructions. They're not very, very different. So let me show you. So in bit manipulation instruction, this comes directly out of the data sheet. You're going to see that we have bit-oriented operations, and in all of them, we're going to go through these instructions, at least 3 of them today. You're going to see that you specify a location in memory that you want to operate on, and then you specify B. This is not D, so this is the bit number, and I'm going to show you what it is. It's the bit number you want to manipulate within the 8-bit. So a few minutes ago, what we did is we manipulated bit number 01, for example, or 2 or 3. Like, we manipulated a certain bit by just specifying in the mask where in the mask I need to set or clear that. Now I don't do that. I just basically specify its number, and then A tells me which access, and basically this F, if it's like a 10 or 20 or something, is it part of banks or just access memory. So today we're going to cover just the bit clear F, bit set F, and bit toggle F, and I recommend that you actually do the bit test on your own, the BTFSC and BTFSS. They have a couple of applications, but we're just going to clear or just cover these 3 here. Okay, so we're going to cover these 3 again with examples, and we're going to start with the, let's start with a bit set. Okay, or we're going to go through one by one. That's fine. So let's start with a bit clear F. Okay, so clear. Okay, so what we have seen in here, I'm going to keep this example. So this example tells me, well, you have this particular value, and I'm going to store it in that particular location. That's okay. And now let's assume that you really want to clear. So we're doing the clear. I want to clear one of these bits. Let's assume that I want to clear this particular bit. Well, it is clear, so let's do this bit here. So I want to clear bit number 012. So like the way we did it using a mask. Okay, so we went on the mask and we said, okay, 012, and I want to clear this particular one, so we kept it at 0. And what I did is I made everything else a bunch of ones. Okay, so that's 1 2 3 4, and then no 1. So let's count it: 1 2 3 4, 1 2 3 4. Okay, of course you can write this in hex, but you get the idea. So what we did is we said, okay, in order for me to clear that particular bit, I need to do an AND in here. Okay, and we went through that code and we did it. So, okay, so we're going to go through it one by one, and okay, so it did exactly what I expected it to be. It cleared that particular bit, so that made the least significant 4 bits as a 1 in hex, and then the most significant 4 bits as 2 in hex. And that's what we got. We got the 22, 21. So this is fine. Technically, you don't write it in binary when you write the mask. You're going to see that most of the code is going to be written in hex, so you're going to have to figure out what your mask is, convert it to hex, and you're going to go here, look what, like, it got converted to us like by the assembler anyway. It's FB. So if you're reading this code, you know that you're setting certain bits and whatnot, but you really have to figure out what the value of the mask is. And what we're doing here is we're just clearing one of the bits. It's really not very readable if we keep it this way. So what I'm going to do is I'm going to ignore that mask. Okay, so I made it into a comment, and look what I'm going to do. I'm going to use this particular instruction here. So the instruction tells me if you want to clear a certain bit in that particular location, which is 0 10, all you have to do is just tell me that is the location I'm interested in. I'm going to tell you which bit you want to clear. It's 0 1 2, so I'm going to just basically tell it bit number 2, and that 10 happened to be in access RAM. So if I do this, you're going to see that, of course, my instructions are going to change a little bit because I'm using the BCF. Okay, and now I'm going to go through it one by one, and I should see the same exact number, which is 21. So if you guys, hopefully you guys agree that the AND and the mask and the OR and the mask, or the masking method, is a lot more convenient, and so not a lot more convenient, it's a lot more flexible. I can set or clear many bits at the same time. But if I'm just doing it for one particular bit, this particular method makes my code a little bit more readable. So here I know what I'm really doing is I'm just clearing bit number 2 within that location. I don't have to think what the mask is and whatnot. So these particular bits, these particular instructions, the BCF or BSF or any of them, they operate on a single bit. So if you want to clear a different bit, for example, let's assume I want to clear another bit, you can say, well, I'm going to clear that 10, and let's assume that I'm going to clear the very least significant bit, which is basically bit 0 in A, and hopefully you guys will see it. Now I cleared a couple of bits. This is a little bit easier to read, but if you're doing it for multiple bits, it's taking more cycles to actually do the same thing as opposed to masking. So you have the option to use either one of them depending on how you're doing it. So let's do this, and I got the 20, exactly what I expected because I cleared a couple of bits. All right. Okay. So with bit clear F, well, I have bit set to F, which is extremely similar, but instead of clearing a certain bit, I'm gonna actually set it to 1. So let's assume that I want, let's do the least significant bit. For example, I want to go and set this to 1. Well, it is a 1 already, so let's do the second, well, which is bit 1. Okay, let's assume that I want to set that to 1. We're going to do this. This particular instruction, it's exactly the same as saying a mask. Let me just write you the mask that you might have had to use. So the mask you would have had to use is 1, 2, 3, 4, 1, 2, 3, 4. Okay, but you want to set this to 1. You're going to move the second bit to 1, and then you're going to OR the mask with that location, and you're going to have that value. But now it's much easier because all I have to do is just specify which bit I want to operate on, and just tell it set it to 1, and it will do it for me. So let's do that, and the answer would be 1, and another 1 in here, and another 1 in here. That becomes a 7, and then 2. So I'm looking for 27. That's what I'm looking for. Okay, so let's go through those steps one at a time, and you can see that I got the number 27. This is exactly what I expected. Of course, you can set several bits, but you're just going to have to repeat that BSF or just deal with the mask. For example, let's assume I want to set the most significant bit to 1. I can do that. Okay, but in order for me to do it, it's either I'm using that mask with an or I'm going to have to replicate this particular instruction one more time in here, and I'm going to tell it, well, the most significant bit is bit number 7, and you're going to go through it, and I'm assuming that becomes, it's going to be 8 and 2, which is a 10, so it's going to be A7, I think. Let's do that. Yeah, and we got the A7. That's exactly what we did. Okay, so this is bit clear, bit set. Well, bit toggle is exactly the same with the XOR. Like you put a mask, let's assume we're going to go back to this mask, and let's assume that I really want to toggle this particular bit. So all I have to do is just tell it, I'm going to tell it bit toggle F, okay? Bit toggle, it's not F, it's actually G in here. So bit toggle G. So we do that, and I'm going to tell it, well, toggle bit number 1, and hopefully I'm going to get that 27 that we've seen a minute ago. Okay. So we're going to go through it. I think I clicked too quickly. So let me just reset. Okay, there you go. Here, and I got the 27 because it toggled it. Again, it's operating on a single bit. All right. So that was bit manipulation, basically. So we did some logic instructions. We did bit manipulations. They're pretty similar. The bit manipulation is a little bit more restrictive, but they're easier to read. So now I'm going to continue with some rotate instructions. Okay. So the rotate instructions that we have 4 of them, and they're read as rotate left with carry, rotate left with no carry, and rotate right with carry, rotate right with no carry. And I'm going to just show you a few slides on them, and then we're going to implement them because the slides will just make it a little bit more visible. Okay, so let's do this. So I'm going to talk about the rotate left, and so we have a couple of instructions again. So we have one with carry, one with no carry. So what's the deal with the carry? Okay, so rotate left, that means I'm rotating. It's just a register, and I'm just going to rotate. I'm not shifting, I'm rotating. So if I have a value, I'm just going to give you a couple of examples to see the difference. Let's focus on the rotate left with the carry. So I have a register, and it has a certain value. Let's assume that this is the value it has. Okay, a bunch of binary bits, 1s and 0s. So the rotate will actually shift that register to the left by 1 location. Okay, and if I do this, that means this 1 in here, which is the most significant bit because I'm shifting to the left, will get out of the register. So if these 1s and 0s are arranged inside the register and I shift for left for 1 location, that bit will be pushed out. But if we're using the rotate left with carry, that carry bit in here will catch that one, will save its location. Okay, And at the same time, whatever was in the carry, whether it's a 0 or 1, will get pushed back to the least significant bit. This is why we call it rotate. So you can think about it as a circular shift if you've heard that term before. So it's a circular shift. It's not a normal shift, because usually in a shift, if something gets shifted out of the register, that's it. Okay, it gets out. But now what I'm doing is I'm rotating it back, but through a carry. So I'm saving that bit in the carry. Now, if I'm dealing with the rotate left with no carry, what I'm doing is I'm basically ignoring that carry bit. So if I'm shifting the same exact number, but now that one would not be captured by the carry, it will actually go directly to the least significant bit. So let's see, if I actually operate that, let's see the difference between them. So after I do one cycle of this rotate left with carry, you're going to see that that happened to happen exactly how I expected it to be. So I got the 1 0 1 1, which is here 1 0 1 1, and then I got the 0 1 0 0 1 0, and that one got out of the register and it got captured by the carry. So I assumed that the carry initially had a 0 in it. So what happened is that 0 got pushed inside the register F, so I can see it here, which is as that is significant bit. So let's see how different it is from the other one with the no carry. So with the no carry, you can see it's pretty much the same exact operation, but now that one did not get captured by the carry like here. What happened is it got pushed to the least significant bit right away. So you can see the two numbers here that appeared in front of me are pretty much different. They're not the same. So one is with a carry, the other one is no carry. So why do we care about these particular operations? Well, it turns out to be that, well, there are certain applications for it, but one of the applications I can think of right off the bat, especially with the one with no carry, is actually multiplying by 2. So as you might remember from 2300, that if you do a shift to the left, you're multiplying by 2, and if you do a shift to the right, you're dividing by 2. So this actually applies just in the case that the most significant bit here that you're pushing out does not happen to be 1. If you're not shifting out a 1, you can actually tell me that you're multiplying by 2. And you can double check at home. So if you take this number, happen to be 45, and you do this rotate left, no carry. Okay, so when you rotate left no carry, I'm going to take that 0 and I'm going to put it back into the least significant bit. So I did not shift a 1 out of the register, and you can see that that number that I'm going to get here is exactly 90. So you can double check them at home, and you can, with different examples, as long as you're not shifting a 1 out, you basically will be able to multiply by 2. So now let's assume that I want to multiply that 90 by 2. I'll issue the same exact instruction. I don't have it on the slide, but you can test it because I can shift that 0 out. Okay, I'm not shifting a 1 out. If I shift everything out and I put a 0 in here, I expect that I will get 180 decimal. You can test it at home. Okay, so the other two instructions for the rotate is actually rotate right. It's exactly the same, but the shift orientation is a little bit to the other side now. So now these are the same examples, okay? And you can see now what I'm doing is I'm rotating to the right. So this particular bit will get pushed out. Okay, it's going to get pushed out and it will be captured by the C. If I don't have the carry, what you're going to see that it gets pushed out and get pushed back in for the least significant bit. Here again, I assume that C initially had a 0 in it. Okay, so what happened is that 0 got pushed out to the most significant bit all the way from here. Okay, so these are the rotate right. Again, same type of applications. As long as you're not pushing as a 1 out, you're basically dividing by 2. Okay, so if I have this particular number, which happened to be 172 decimal, and I'm not pushing, if I'm doing a right shift, okay, that 0 gets pushed out, get pushed in the other side, and you can see that I got exactly 172 divided by 2, which is 86. And you can repeat it. Let's assume that I want to get 86 divided by 2, which is 43, I think. Okay, you can do that at home, and you can see that that 43, you're going to push that 0, and you're going to push it back in here, and you're going to shift everything to the right by 1 location. So you can do 2 to the power n, and n is the many rotations that you have. So you can now multiply and divide. Remember, the PIC 18F does not have a divider. Okay, so now this is a very easy division if you just care about dividing by 2. So you can actually use these instructions to do that. All right. Alright, so now what I'm going to do is I'm going to test these just to make sure that I'm getting exactly what I'm supposed to. So let's see, I'm going through the slides one more time so that we can actually get the same numbers. Okay, so let's assume that I want to do that particular slide in here. Okay, so I'm going to move that one into some location in memory, and that location is going to be 10. So let's write that number here. So I will do, let me just make them that way so I can see all of them. Okay, so we're going to do 1010 1101, and that's in binary, so we're going to store that, and I'm going to store it in location 10. That's fine. And now instead of doing, I don't need the masks or anything, what I'm doing is I'm doing a couple of rotations. So let's assume that I want to rotate left with a carry of location F, and that location F is that 10. Okay, and I'm going to say, well, my destination, let's say that destination has to be the work on register. That's where I want it to be, and that's A, because I want to preserve that value to do something else with it if I wanted to. Okay, so the answer, which is here, which is 0101 1010, I said here that it's in location F, but that means I set the location or the destination for the answer to be F, but for now it's just going to be the W, and you're going to see that the carry is going to be set to 1. So if I carry this one here, or I debug it, okay, so we're going to do this in here, do the debug, and I need to see what the shortcut for this here is. The shortcut is F7. Okay, so we're going to do that F7. Okay. Yeah, it's F keys. Okay, so we're going to do F7 and F7, and you can see what happened is here in F7 you can see that the value at 10 did not change because I did not store that number in it. What I did is I stored it in the WA, and what the working register told me, it's actually 5A. Let's see it. This is A, which is 10, 8 and 2 is 10, and this is 5, which is correct, so I got 5A. And more importantly, the carry happened to be 1. So now if I do the same exact thing but without that carry, let's assume no carry. Okay, so we rotate left, no carry, and I do the same exact thing. You can see, okay, so we can do that. We'll do 1 and 2, okay, and then the no carry, you can see that that value does not change because I'm storing it on the working register. And you can see the working register now has a different value. What it has the number 11, which is a B, and it has a 5, so it's 5 and B. And you can see that the carry did not change because it's a 0. The previous operation did not generate a carry because I'm not using a carry, and so forth. Of course, you can implement this. You can double check it. For example, you can do a different number. For example, I think I put, well, let's do that here. You're going to see that is 0010 1101. Okay, and you can do the same exact thing that I just did right now, but I'm going to care about with the no carry. Okay, and now I'm expecting to see that inside the working register, I'm going to get the double of 45, which is 90D in decimal. Okay, so 1, 2, and 3, and hopefully this is 90D, which is, I think it's right. Let's see it. Oh, well, again, I got an error because I forgot to put the binary in here. You have to tell it that it's binary, so this isn't the right number. I usually do this mistake many times. Okay, that number did not make sense to me. So, okay, we get that, and now it makes more sense. So this is an A, this is a 5, this is an A, this is a 5. That's correct, and I got double the number. You can do the same thing with the rotated right. You can test it at home on your own. I don't want to spend more time on it. Okay,